Hello everyone, my name is Samuel Finder, and I'm going to be taking you through a testing time travel where we will explore the development of software testing over time and how that is now integrated with modern DevOps. Imagine the scene. It's December 31st, 1999, as the world eagerly awaited the stroke of midnight to usher in the new millennium. Behind the scenes, our software systems were running on a ticking time bomb. You see, many systems use the two-digit date codes such as 99 for the year 1999. When the clock struck midnight, there was a real fear that these systems would interpret 00 as 1900 and not 2000. The potential for chaos was palpable. This looming disaster wasn't just a hypothetical scenario. It was a very real threat. Organizations across the globe realized that if left unchecked, the Y2K problem could lead to system crashes, financial meltdowns, and widespread chaos. This realization sparked an unprecedented testing boom. Teams scrambled to identify and fix potential Y2K-related bugs before the clock struck midnight. In the years leading up to the turn of the millennium, the public gradually became aware of the Y2K scare, and individual companies predicted the global damage caused by the bug would require anything between $400 million and $600 billion to rectify the situation. The Y2K problem wasn't just a glitch. It was a wake-up call. Suddenly, good enough wasn't sufficient. We needed rigorous testing practices, and we needed them fast. This pivotal moment marked the beginning of a testing boom. Organizations embraced the importance of thorough testing, leading to the development of modern testing frameworks and methodologies that we rely on today. To truly grasp the current landscape of software testing, and it's insightful to rewind to one of the earliest documented instances, NASA's Project Mercury. Running from 1958 to 1963, Project Mercury marked NASA's inaugural manned spaceflight program, employing IBM 790 computers for critical tasks such as calculations, navigations, and life support. In those early days, testing wasn't standard practice. Coders were tasked with producing flawless code without the benefit of extensive testing procedures. Despite this, Gerald Weinberg, a trailblazer in software engineering, was a visionary ahead of his time, serving as a lead on Project Mercury's software development. Weinberg advocated for quality assurance in testing, concepts often disregarded by his contemporaries. His efforts ushered in a paradigm shift in software development and testing methodologies. By the 1960s, the tech industry was experiencing explosive growth. To expedite development, companies hired a surplus of engineers. However, the availability of skilled engineers was limited, resulting in low-quality, bug-ridden code that fell short of the high standards set by Weinberg. This rush to release was a contributing factor to the infamous Y2K problem. These historical insights remind us of the importance of thorough testing in software development. To truly grasp the evolution of testing practices, let's delve into the realm of software development methodologies. We start with the structured and linear approach of waterfall, which follows distinct phases from requirements gathering to maintenance. In waterfall, each phase must be completed before moving to the next, often resulting in lengthy release cycles. Testing in waterfall typically occurs late in the cycle, leading to limited feedback and an increased risk of defects slipping through the cracks. This rigid model can hinder the ability to adapt to changing requirements, making it challenging to deliver high-quality software efficiently. Contrastingly, agile methodologies such as Scrum and Kanban introduce a paradigm shift in software development. Agile emphasizes iterative and incremental development, allowing for continuous testing throughout the process. This approach enables quick feedback loops, facilitating the early detection and resulting of issues. Agile teams can adapt to changing requirements, delivering valuable software increments in short cycles. This iterative nature significantly improved the quality of software and responsiveness to customers' needs. As we progress along the evolutionary path, we encounter DevOps, the collaborative marriage of development and operations. DevOps builds upon agile principles by emphasizing collaboration, communication, and automation among development, among development, operations, and testing teams. Continuous integration serves as a cornerstone of DevOps, automating the process of integrating code changes into a shared repository and running automated tests. This ensures thorough testing and validation of code changes as soon as they are introduced. Additionally, continuous development in DevOps automates the development process, enabling swift and reliable release of code changes to production environments. By automating testing and deployment, DevOps eliminates manual errors, reducing deployment time and increasing release frequency. This seamless integration of testing practices within DevOps workflows further strengthens software product quality and reliability. Continuous integration extends beyond code integration. It encompasses continuous testing to uphold the highest quality standards. When a developer makes a code change and commits it to the shared repository, CI initiates the process. This code is automatically built and tested, which includes running unit tests, integration tests, and sometimes user acceptance tests. This automated testing forms the backbone of CI. There are multiple benefits of CI testing. Firstly, it enables early bug detection, catching issues as soon as they occur, rather than awaiting until the end of the development cycle, reducing debugging time. Secondly, CI ensures the consistent code quality by checking every commit against predefined standards, maintaining a high level of quality throughout the project. Lastly, CI provides a quick feedback loop for developers, offering immediate insight into the impact of their code changes, facilitating rapid iteration and improvement. CI is a fundamental aspect of DevOps practices, automating code integration and testing processes. It aligns seamlessly within the DevOps principle of shift left, where testing occurs early in the development lifecycle. DevOps ensures that our CI pipeline is not only efficient and reliable, but also seamlessly integrated with our deployment process. This integration of CI and DevOps practices ensures thorough testing, reliability, and readiness for deployment at any moment. As we've explored the collaborative synergy of DevOps and the role of continuous integration, it's essential to delve into specific tests that run on these pipelines. One of the foundational tests is unit testing, a cornerstone in the CI pipelines of major corporations. These tests scrutinize individual components, functions, methods, or classes in isolation from the rest of the system. Developers leverage tools like JUnit, PyTest, or Jest, just to mention a few, to craft meticulous tests that verify each unit's behavior, enabling early bug detection and streamlining the debugging process. Unit tests cover various scenarios and edge cases, ensuring that units behave as expected under different conditions. In the CI pipeline, unit tests are executed automatically within each code commit, providing rapid feedback to developers. This automation ensures that new code changes do not inadvertently break existing functionality, maintaining code integrity and preventing regressions. Unit test is not merely a checkbox in the development process. It is a fundamental practice that fosters code quality, accelerates development cycles, and ultimately contributes to the stability of software products at large companies. As we've explored the synergy, as we progress through the CI/CD pipelines, integration testing emerges as a crucial phase, ensuring the seamless interaction of various components or services. Integration testing focuses on testing how various components work together as a unified system. It verifies the interfaces and interactions between different modules or services to ensure they function seamlessly when integrated. Integration testing occurs after unit testing and validates the correct behavior of the system as a whole, catching issues that arise from the combination of components. This testing stages holds a pivotal role in validating system-wide functionality and pinpointing integration issues early in the development lifecycle. Common use tools like Postman and SoapUI enable developers to execute integration tests effectively, employing techniques such as API testing and database integration testing. The benefits of integration testing are substantial, allowing for early detection of integration issues, which enhance overall software quality and save time and resources by addressing problems before production. Integrated seamlessly into the CI/CD pipelines, integration testing can be run with every code change, providing continuous validation and quick feedback for developers. For example, consider testing the integration between a front-end application and its back-end API. By mocking API responses, validating data flow, and checking error handling, integration testing ensures that harmonious operations of front-end and back-end components. In continuous integration, CI pipelines, offer a diverse range of tests that can be integrated to ensure software quality. While some tests are automated and seamlessly fit into the pipeline, others require manual intervention to achieve optimal results. Other automated tests often found on a CI pipeline include end-to-end testing, which serves to validate the complete application workflow by utilizing scripts that simulate real user scenarios and interactions. Tools like Selenium WebDriver and Cypress are commonly used for this purpose. Security testing can be another automated process added to a pipeline, aiming to identify vulnerabilities and ensure application security. On the other hand, certain tests are better suited for manual execution outside of the pipeline. User interface testing, for example, is vital for validating UI elements, layouts, and user interactions. Testers manually interact with the UI, visually inspecting and verifying its behaviors. This manual approach is preferred for complex UI interactions, where automated scripts may not capture all the nuances. Considerations for manual testing in CI pipelines include scenarios involving complex UI interactions, where human intuition is crucial for thorough validation. Usability and user experience testing also benefit from manual testing, as assessing user workflow and overall experience often requires subjective feedback. In conclusion, DevOps has revolutionized the testing process by introducing automation, resulting in a more efficient and rapid validation of software functionalities. However, despite this efficiency, manual testing remains essential for certain aspects of software quality assurance. While automated tests such as end-to-end and security testing offer swift validation of core functionalities, manual testing like UI testing, exploratory testing, and usability testing provide crucial subjective feedback on user flow and overall experience. This combination of automated and manual testing approaches within the CI pipelines ensure comprehensive software quality assurance, leading to robust and user-friendly applications that meet high-quality standards. It's important to recognize that even with the efficiency of CI pipelines, there's still tests that necessitate manual inspection, emphasizing the ongoing need for human intervention in the testing process. Thank you.